Okay, so we're going to continue on in Unit 3, and we're going to talk today about molar mass. So let's say I have a Chem 122 class that has 200 students. One day, I want to bring in jelly beans, and I want each student to have 10 jelly beans. How many total jelly beans do I need to bring? So I have 200 students, and I want each student to have 10 jelly beans, so 10 jelly beans per student. So I would need to bring in 2,000 jelly beans. And it would take me a long time to count out 2,000 jelly beans. I probably have papers to grade or something else to do that my time could be better used. So it turns out that there are 400 jelly beans in a pound. And this is Jelly Belly brand jelly beans. My husband and I went on a tour of a Jelly Belly factory several years ago. And I've always liked Jelly Bellies. They're my favorite jelly bean. But we were both amazed. And I don't know why this shouldn't have been a surprise, but at how much sugar they put into jelly beans. There are these giant drums, and they put in the sugar, and they heat it up, and then they tumble it with more sugar, and it was just a series of drums that rotated with more and more sugar, and then there was a polishing sugar, and then the different dyes and everything and flavors. But my husband and I just laughed at how much sugar tumbling was necessary. Anyways, so there are 400 jelly beans and 1 pound of Jelly Belly jelly beans. So if I want to bring in to my class Jelly Belly brand jelly beans, and I have 200 students, I want each student to have 10 jelly beans. And I know instead of counting them out, I can weigh them out. So if I want 2,000 jelly beans, and there are 400 jelly beans and 1 pound, I can figure out how many pounds of jelly beans I need to weigh out instead of counting them out, because my students wouldn't want me to count them out, right? With all the germs and sickness and yeah. So let's see, 420. So that would be 5 pounds. So I need to weigh out 5 pounds of Jelly Belly jelly beans to bring to my students, and probably a little bit extra, right? If I'm going to eat some on the way to class. But we kind of use this reasoning. Well, we do use this reasoning in chemistry. It's a lot easier to weigh out atoms than to count them out. And the reason is atoms are so small. And there are microscopes that can be used to count atoms, but you're going to spend a ton of time counting, and then you'll lose count. It's like when I knit and I casting on, and I swear I count about 6 or 7 times to make sure I have the right number of stitches, but drive everybody in my family crazy. What did I just count? Anyways. So it's a lot easier in chemistry to weigh out chemicals and figure out how many are present based on an Avogadro's number, which we'll talk about in a second. So if you look on the periodic table, which, sorry, I didn't have it right here, sorry. On the front of your textbook, there is a nice, convenient periodic table. And if you look at phosphorus, there is a number that's written underneath phosphorus. Not the atomic number, but this. And this is the atomic weight. So in the atomic weights, we just round to the hundredths. So this is 30.97 is what's listed for phosphorus. And it turns out that 30.9738 grams of phosphorus is 1 mole of phosphorus atoms. And so in chemistry, the mole is kind of like the dozen. So, and as in baking, you get a dozen donuts, that would be 12 donuts. And so the mole is really large. The mole, 1 mole, and I have this on the next page, equals 6.022 times 10 to the 23rd atoms. So that's a lot. It just gives you an idea of how small atoms really are. 6.022 times 10 to the 23rd. And it turns out, chemists celebrate Mole Day. And anybody can celebrate Mole Day, but I always think this is funny. So Mole Day is October 23rd. So you get that from 1023. And it starts at 6:02 a.m. Sorry, I always joke around with students that you could try to eat a mole of donuts on Mole Day, starting at 6:02 a.m. on October 23rd. I don't think you would get very far because a mole of donuts is a ton of donuts. So this number, so Avogadro's number is 6.022 times 10 to the 23rd. And that's, Avogadro is the one who discovered this. And it's amazing that he was able to come up with this number and determine it. And you can read about the experiments he did to determine what a mole is. It's quite remarkable. And it's a lot easier than counting out atoms. So if you have 1 mole of NaCl, table salt, that means you have 1 mole of sodium, 1 mole of chloride, and that's because of the subscripts here. And the abbreviation for mole, by the way, is not very great. It's MOL. You get rid of an E. But if I have 1 mole of C2H6, then I have 1 times 2 moles of carbon, and 1 times 6 moles of hydrogen. So, and I answer this question right here. If I want to make 1 mole of sodium chloride, how many moles of sodium and chloride do I need? So you need so to make 1 mole of sodium chloride, you need 1 mole of sodium and 1 mole of chloride. Which brings us to molar mass, this definition. So the molar mass is the mass of 1 mole of substance. So mass of 1 mole of substance. I say substance because it could be atoms, it could be ionic compounds, it could be covalent compounds. The units on molar mass are grams per mole. And I like to write it, my preferred way to write it is grams over moles. So to calculate the molar mass of a substance, you're just going to add up the atomic weights from potassium and fluoride. So it's a 1-to-1. So I'll show you how to do this. So if you look up the atomic weight of potassium, it's 1 times 39. And I'm going to round to the hundreds, everything except hydrogen. Fluoride is 1 times 19. And then I'm going to add that together, and I'll come up with the molar mass of potassium chloride. So 39.1 plus 19 gives me 58.10, and my units on that are grams per 1 mole. Later on, we're going to use molar mass as a conversion factor. So if you get in the habit of writing molar mass like this with its units, it will be a lot easier to carry out those conversions. Okay, let's do C12H22O11. So carbon is 12.01, and I have 12 carbon. So 12 times 12.01 plus hydrogen, which is 22. Hydrogen, you go to the hundreds. So that's, or not the hundreds, the thousands, sorry, 1.008 plus oxygen, 11 times 16. So you're going to add all those together. And if you do this in one fell swoop, you're more than welcome to. Just be sure to use your parentheses on your calculator. 12 times 12.01 plus 22 times 1.008 plus 11 times 16, and you get 342.29, and we'll round that. 342 to the hundreds, 342.30 grams per 1 mole. Okay, and the last one, ammonium dichromate, ammonium NH4 plus, dichromate Cr2O7, 2 minus. So our formula will be NH4, 2, Cr2O7, and so we've got nitrogen, hydrogen, chromium, and oxygen. So nitrogen, 1 times 2, it's going to be 2 times 14.01 plus hydrogen, 2 times 4 is 8 times 1.008 plus chromium, 2 times 52, I believe. Where are you, chromium? Yeah, 52. And then oxygen, 7 times 16.00. So enter that into your calculator with parentheses, or you can do each step individually. And you come up with 252.08. So that concludes the lecture on molar mass. Do your practice problems and your reading. Will help when you practice this. It's a good idea to have a firm foundation in molar mass because we will be converting between grams and moles in the next lecture. So I will see you next time for more Unit 3.